interpreting and sketching graphs of functions and relations. So in math, graphs are one way to show a lot of information in a short amount of time. So here we have a scuba diver's dive. On the y-axis we have their depth. That's the dependent variable. On the x-axis we have the time. Okay? That's the independent variable. Does this scuba diver have oxygen? Yes. If they otherwise, can you see that they start at the surface because they're at a depth of 0? Okay? Sometimes graphs go counter to our intuition. Because as the graph goes up, what is the scuba diver doing? Going down, getting deeper, right? But that's because the depth of the water is shown there. And then it's only after 30 minutes that they come back to the surface. So I would hope that they have oxygen, right? Otherwise, this is probably not very possible. So if we answer some questions here, how many minutes did the dive last? 30 minutes in total. When did the diver stop her descent? At what times? Okay. Can you see they stopped descending here where it's flat? From 4 minutes to 8 minutes. And from 10 minutes to 14 minutes. And we can make a story. We can say, oh, I think here they saw a very pretty fish. And so they just looked at that fish for 4 minutes. And then they went, and maybe this is the very bottom. And so at the bottom they stopped descending because they were walking around on the bottom looking at the shipwreck that they found and picking up gold coins. You know, because that's what all scuba divers do all the time. Pick up gold coins. So it's very exciting. And then at this point, right, at 14 minutes, the little light comes up saying, you're almost out of oxygen. And so they just swim as fast as they can back to the surface. Well, maybe it wasn't super fast, right? But they said, maybe I should get back to the surface before my oxygen runs out. What was the greatest depth the diver reached? According to the map or the graph, the greatest depth was 20 meters. How many minutes was the diver at that greatest depth? Well, we already know that they stopped there from 10 minutes to 14 minutes. So they were at that greatest depth for 4 minutes. So we can kind of get a story by just looking at the graph. So the properties of a graph can also tell us things about the graph. So we've got a steep increase, a steep decrease, no change there where it's flat, another increase but not as steep as before, a very steep decrease, and then a moderate decrease. So we could say, okay, we've got distance and time. Okay? So we could make up a story. This is distance in meters. So what could we have as a story? This is the distance from my desk. Okay, you are currently 5 meters away from my desk. The bell rings and you want to get out of here. So you run, start running out. At this point, 1 minute, like you're running for 1 minute, but you're not running very fast apparently, because in 1 minute, you travel from 5 to 11, you travel 6 meters in 1 minute. So even though it's a steep increase, we're imagining running out of class 6 meters in 1 minute. You could be crawling out of class, maybe dragging yourself with your hands, perhaps. And then once you're at 11 meters, you go, oh no, I forgot all my books. And so you claw your way back into class. It takes you 2 minutes to get 4 meters back into class. And then you stare at your desk blankly for 2 minutes, realizing that, all right, here you realize that you can't find your books, even though they're right on top of your desk. You finally find them and start leaving again. And then someone tells you, you know what? That was just the second bell after recess. Class isn't over. You need to come back. And so you slowly come back, and eventually it takes you 14 minutes just to get to my desk because you had an assignment to hand in. Okay, so this probably isn't a realistic situation for the graph, but it shows how different parts of the graph. Apparently, you were 4 meters away from my desk, and it took you another 7 minutes to slowly hand in your assignment. But you walked this moderate decrease, you walked at a constant speed from your desk to my desk over 7 minutes, slowly getting there until finally you could hand in your assignment. So each point on a graph represents here a bag of popping corn. So we have the cost and we have the mass. Which bag is the most expensive? And what does it cost? Bag C is the most expensive. How much is it? $7. Right? That's that fancy popcorn that's got flavors built into it. Maybe they've invented some sort of popcorn where it's like a donut with jelly in the middle, but it's popcorn that has actual melted butter right in the middle of it. It's half cut off on yours. Should we skip? Oh, yeah. So we can only answer part A and part B. Which bags have the same mass? Can you see that on yours? Yes, you can. The same mass would be D and E. And that's where yours gets cut off. So we're going to cut off this question and move to the next one right away. But we could answer these. Which ones cost the same? What is the cost? And figure it out from there. I think when I put the page numbers on, it shifted everything and then threw the graphs off a little bit. But we can see this one. Jenna likes to do cross-country skiing. Saturday, she skied the Blue Ptarmigan course in 1 hour. Following graph shows her speed along the course. So here's her speed in kilometers per hour. And then she started at 10. So this is time in minutes after 10 o'clock. What is her speed at 10:10? So I'm going to mark that on my graph at 10:10. That's point B. What would you estimate her speed to be at that point? Does it look like 4 or does that look like 3? 3? Okay. Three kilometers per hour. What is Jenna's speed at its maximum. And what time? It looks like the time is going to be at point A, right? That's the maximum at point A. We would say at 10:05, her max speed, we'll say that's close enough to be 5 kilometers per hour. Part C, describe what happens in terms of her speed between 10:10 and 10:40. What's happening to her speed during that time? The speed remains constant. It doesn't change. So it looks like Jenna started off and just started getting faster and faster and faster, hit 5 kilometers an hour, and was like, whoa, this is too fast for me. I'm going to slow down a little bit, and then, okay, I can maintain 3 kilometers per hour. And she did so for 30 minutes. That's pretty amazing. Okay, I'm imagining this trail then being pretty flat in order to maintain no hills, because if you get a hill, you're going to slow down. You're going to go downhill. You're going to be like, yeah, speed up, relax. Okay? What happens between 10:40 and 10:50? Well, 10:40 till about 10:44, she slows down. So we can look at 10:40 to 10:44. That's where she slows down. And then from 10:44 to 10:50, what's happening there? She is stopped. She doesn't move. She just, oh, I'm done. Sitting down, taking off my skis, getting a drink of water from half an hour of good exercise. So these first couple examples, we were given graphs, we looked at the graphs and interpreted them. Sometimes we're given a situation. So in this next situation, you get on a Ferris wheel. The wheel has a diameter of 10 meters, and the seats are 1 meter above the ground at their lowest point. It takes 60 seconds for the wheel to complete 1 revolution. I would like you to graph time along the x-axis and height along the y-axis. Do it in pencil and come up with your own graph first, and then we'll discuss it, and I'll come around and look at some of them. Maybe I'll even take some pictures of some and put them up on the screen. So you're on your Ferris wheel. We put time along the x-axis in seconds. We put height in meters. The first thing we have to decide is what kind of scale do we want to make? What is the data that we're talking about? Okay, it takes 60 seconds for a wheel to complete 1 revolution. So what I did on my scale is I did up to 120 seconds so we could see going around a Ferris wheel twice. The height, we start 1 meter above the ground, and the wheel has a diameter of 10 meters. So the highest you're ever going to get is 11 meters. Because you're starting at 1 meter, right? We can draw. Sometimes it's helpful even to draw a picture off to the side of the situation. So here is my Ferris wheel, it starts 1 meter above the ground. It's good for a Ferris wheel not to start right on the ground, because then your legs go into the ground every time you come around, and I don't think that would be very comfortable. Okay? It's also probably good not to start up too high, although they do have some different places where they have like Ferris wheels really high up, so it's supposed to be scarier. All right. And then because the diameter is 10 meters, diameter is all the way across the circle, does it make sense that the highest you'll ever be is 11 meters? So sometimes drawing an actual picture, I guess we should put spokes on here, otherwise it's not very realistic. Some fancy red chairs. Oh, nice. No, I just said realistic. Wheelistic would be awesome, though. Okay, so there we've got our picture. You get on. How high are you when you get on? 1 meter. So here's our starting point at 0 seconds. It starts there. Then they go around. It says it takes 60 seconds to complete one full revolution. So where are you going to be at 60 seconds? 1 meter. Now if we make a graph just by joining these lines, it'll be a straight line, but that straight line would mean you always stay at 1 meter. But that's not true. Let's talk about some different points. Let's draw you. Here we go. Here you are, super happy to be on the Ferris wheel. Whoa. No, wait for it. There we go. There we go. Yee! There you are. How long is it going to take you to be up there? 30 seconds. So we can go on to our graph and say, I know at 30 seconds, I'm going to be at 11 meters. How long would it take you to get to there? 15 seconds, half the way to 30. So I could, and how high would you be there at 15 seconds? So I'm at 15 seconds here. How high should I make that dot? 6. Because it's halfway to the top, so up 5 meters, but you started 1 meter above the ground. We could keep going, ding, and you would be at that point at what time? 45 seconds. So you could go 45 seconds and put a point there. Could you see that this would repeat itself? You get back down to the bottom, and then at 75 seconds, you're back there. At 90 seconds, you're back at the top. This is assuming, of course, that it doesn't stop. Usually, you get on a ride like this, and they go around and around for a little bit, and then they start letting people off, so you like stop at the top, get so excited. So now when we have these points, now we have to decide what's going to happen between the points. And coming around, I noticed that a number of you just drew straight lines through them. Okay? If we draw straight lines through them like this, zoop, zoop, this would be a very jerky ride, because you would get to the bottom and boop, you would immediately start going up without hesitating at all. But a Ferris wheel ends up being a little bit smoother. So the actual graph would go up, slowly flatten out, and kind of curves through these points as you go. Because as here you are, right, here you're going up fast, but then as you get to the top, you're not going up as fast as you were. Wear a seatbelt. Oh my goodness. Yes, right? What could make this ride more exciting is we could change the units. We could change the units to kilometers. So now you're going 11 kilometers up into the sky, right? And we could change the time to milliseconds. So you go 11 kilometers up in the sky and come back down within 60 milliseconds. You know how fast you would have to travel? Okay, I think currently this person would die. Oh well. Sasha goes for a ride on her bicycle. She accelerates until she reaches a speed of 20 kilometers per hour. Then she rides at this speed for 30 minutes. Sasha arrives at the bottom of a hill, and her speed decreases to approximately 5 kilometers per hour for 10 minutes. This one's cut off again? Okay. You don't have the whole graph. You have the question, though? Okay. Yes, you just have a tiny bit of the graph. So we'll do this one together. I think on your next page, you have just a blank space. You can add a graph on the next page. We want to sketch a graph of her speed as a function of time. So you don't need to put all the grid marks in there. What we're going to have here, the independent variable, is the speed. And the speed is measured in kilometers per hour. And along the axis down here, we're going to put the time. And the time in this question is measured in minutes. Reaches a top speed of 20 kilometers per hour. Okay. She travels at that for 30 minutes. Another 10 minutes, another 10 minutes. So maybe we'll go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And our top speed is 20 kilometers per hour, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 20 kilometers. So it doesn't tell us how long it takes her to get to 20 kilometers per hour. But she's accelerating. So she's starting at 0 kilometers per hour and accelerating until she gets to 20 kilometers per hour. So we can start here at 0. How many minutes do you think it's going to take her to get to 20 kilometers per hour? She constantly, like within 10 minutes, she could probably get there? Okay, so we'll say she accelerates constant speed until she gets to 20. She then travels at that same speed for 30 minutes. So she's at 10. 30 minutes would get her across to there. Okay? She arrives at the bottom of a hill, and her speed decreases to approximately 5 kilometers per hour for 10 minutes. So we need to decrease. Let's say it takes her 10 minutes to decrease that speed, because again, it doesn't tell us, so this would be something that we would have some options for. And she's going to stay at that speed for 10 minutes. And she's cycling up a hill at that time. She stops at the top of the hill. Okay, we're not going to, why would this be bad for stopping? Almost instantly. Yeah, well, it might maybe be like at the top of the hill, there's a bus she runs into. That would not be very good. So we we need to make her stop more gradually. And then she rests at the top of the hill for 10 minutes. Yeah, you won't want it to happen instantaneously, okay? One of the things, if we go back to the previous graph for the Ferris wheel, sometimes because people think that Ferris wheels go round and round, sometimes I've seen graphs for Ferris wheels go like this, because you're going around and around, okay? This would mean that you're going back in time, okay? There's also some bad things, like on this graph, you're here and you're here at the same time, right? That would be bad. You'd be like, oh, my legs are down there and I'm up here. Okay? So we can't go back in time. We can't be in more than one spot at once. Okay, if you're in more than one spot at once, you're not a function, right? And that wouldn't be very good either. It's just a relation. So something that is, okay. So we're going to stop here.